transition this and you can take over.
All right. Well, yeah, thank you all for coming tonight. My name is Stephen Estrella. I'm the Director of Business Development at Freedom Photonics. We're a company kind of just down the street. My title is pretty ambitious, so hopefully I will not leave you disappointed. But I'm going to talk about a few things here. So maybe give a little bit of background about kind of who I am. And for those of you maybe who aren't as familiar with photonics, give you a little bit of a light introduction, nothing too crazy. And then kind of go into some examples, like how is this actually used, and what are some of the frontiers that this is trying to be applied towards. So like 6 years later, I decided to kind of go back to graduate school, and wasn't until about 2018 I kind of graduated, did a master's degree there, and then followed on by a doctorate degree at UCSB. And since then, I've kind of been working, you can see kind of on the bottom chart, sort of the professional development versus on top, sort of the academic development. So today, I work as a director of business development. What does that mean? It means I basically talk like this. Now I talk to people, I talk to potential customers, but I'm also looking at what I'm going to show you, sort of how does this technology kind of get applied, and who might be interested in it, and kind of formulate those partnerships. I kind of created this map because I thought it's pretty interesting. So I'm not sure exactly who came up with this nomenclature, but we're kind of known as what's called the Silicon Beach. Okay, unlike the Silicon Valley. So why is that? Well, I'm specifically highlighting like other photonics companies that are here in the area. Maybe some of them you might recognize from the logo, but there's someone like Thor Labs. They're kind of in Santa Barbara. There's us. Kyocera is actually right down the street here from us, right on Pine Avenue. But there are a lot of other companies, and the reason why there is such a high density of these types of companies is really because of UCSB. So a lot of the technology that these companies are commercializing have kind of spun out of the university, and our company, Freedom Photonics, is really no different. A lot of what we have developed has started in the labs there and has transitioned, I think, successfully commercially. So a lot of the companies that you see here, like, okay, this, you actually can't see this, but this is HPE, very large organization. And of course, I'm not highlighting all the other like defense companies that are here, like, Northrop Grumman, Lockheed, FLIR, Raytheon. I mean, all those guys are here as well. And they're actually working in, I would say, analogous technology. They're really looking at infrared technology, infrared detectors, cameras, things like that. But we like to think of ourselves as kind of all one big happy family. It's a very large ecosystem, a lot of problems to solve, and that means that there's opportunities. So I thought this was kind of interesting, just to kind of show you guys, like, we're not necessarily like the only photonics company in town. There's actually quite a few that are located here. All right, so like, what is photonics, right? So yeah, we're not going to get into multivariable calculus, but if you knew that, that would be a great starting point, right? These equations are obviously used to describe the interaction between the electric and magnetic fields and how they propagate, but we're not going to delve into that. So I think what's interesting to start with is really just like the definition, like what is photonics, and it involves kind of a lot of things. So you're generating, you're detecting, and manipulating and modulating light, right? And so these light waves, basically, they're propagating electric and magnetic fields, and that's like the wave interpretation of them, right? But they can also be described by a particle interpretation. So for this talk, we're going to think of it in terms of like propagating waves. the use of like guiding light kind of dates back, many centuries. You can kind of see sort of the history from when we kind of first started, discovering that you can actually guide light through some type of medium, all the way to when, like in the 60s, the first sort of laser was actually demonstrated or invented. And since about that time, there's been a lot of development. And really the focus has been on how do you make it practical? How can you shrink some of these components down? Because, the first lasers were giant, like tabletop things. But, today you have VCSEL type lasers that are in your phone, right? That are used for recognizing your face. So it's come a long ways from just giant sort of huge components to like really shrinking that down. And I'll show you some examples today of like what these devices kind of look like. So a lot of, the physical principles, you're familiar maybe looking to a pool, right? You see sort of diffraction, but the fact that we can utilize what's called total internal reflection is how we actually guide light. So this is like a big example, but like we're sending light down waveguides that are really, really tiny, through optical fibers. These are about the diameter of like a human hair, right? So probably coming into this building somewhere is going to be like an optical internet coming off the street, right? I mean, the backbone of the internet is entirely fiber optic based. We don't have fibers, well, some people do, not in my house, fiber directly going to the home. And so it's come a long ways, and I think it's pretty exciting. I like kind of showing sort of some of the artwork associated with photonics, right? So, is this the Pink Floyd album? No, but you're probably familiar. But we make use of other principles in light. So there's like guiding light, right? There's also like dispersion. So how do materials interact with light? That's pretty important. Some colors travel faster than others. You can kind of see sort of an image of that there. So when we put these things together, this is like an example today of what a photonic integrated circuit might look like. This is something that I worked on many years ago. But this is a device that actually has a lot of different functions, right? So consider this device to be kind of like, the early days of microelectronics, like a couple of transistors that are on a device, right? Making like, op amps and things like that. We're not too far from that necessarily. Maybe we have, hundreds of components that can be put on a particular integrated circuit, but it's very challenging. This type of device, this is like in a different type of material that can generate light. It can also detect light. Unlike silicon, which is primarily used for microelectronics, those are where all of your computer chips, are kind of made today. We actually still use that process to make, photonic integrated circuits, but it has its challenges because you can't generate light from silicon. Whoever solves that problem will get a Nobel Prize, but so far no one has done it in a practical sense, in a scalable way. So we take these devices and we put them into components, right? Like, I can't just give somebody an integrated circuit that's a couple of millimeters. It's very fragile. So when people typically look at like what does an optical component look like, you're probably going to see something that's about the size of a quarter, right? These things get soldered onto PCB boards. They go into like slot cards. They go into racks, right? Fiber optic cables come in, connect to them, and so on. So you kind of get an idea of like what do these pieces sort of look like. All right, now that we have that introduction, so our company is actually owned by an automotive LiDAR company. It's called Luminar Technologies. It's a publicly traded company. They're in Orlando, Florida. So it's only natural that I would talk a little bit about LiDAR. So the problem that we're trying to solve as a company in general is like, how do you keep a driver safe, and how do you keep those around you safe? One of the typical examples is you need to be able to see like a blown tire. A tire is very dark, so it doesn't have very high reflectivity. And if you see something maybe 250 meters out, but you're traveling at 65, 70 miles an hour, you need to be able to see that and stop in time and not hit that, right? So today this is kind of being done many different ways, but the promise here is that we can do it with using light. The reason is because you can have much longer range, so I can see farther, and I can also have higher resolution, so I can actually determine, is it a person, Is it a tire? Is it an animal? Is it a car? Is it a bike? I need to be able to like distinguish that, because that might influence what my next course of action sort of might be. And the way it's been kind of done today, and especially with like even the VCSELs that you have in your phone, not enough power to be able to send light, far enough out and be able to gather all that information. So the technology that we are developing are these really powerful lasers that are still eye safe, right? So you don't want to be blinded by it. You can't have just a bunch of lasers just shooting all around, right? The wavelength actually matters so that you do not ruin like the cornea of your eye. And so that's been like a large development as to how do you make really good lasers where you can apply these to these LiDAR type sensors. So today we are actually doing that. So with this company, we are supplying sort of the laser component here, and within sort of the family of companies that are owned by Luminar, we address sort of all these other components. So one example here, again, it's kind of relative to the size of like a dime. This would be, a laser chip, right? Very, very, very tiny. And we basically mount this to an integrated circuit that supplies kind of like all the control signals. So we need to like send pulses of light. So that's what this device does, is it pulses the laser and sends it out. So it goes into something that, this is a typical package actually. Jürgen knows what these look like, but these are called butterfly packages. I don't know what engineer thought this was looked like a butterfly, but there are these leads basically that kind of come out on the sides, and I don't know, somebody thought long ago that these should be called butterfly packages. But anyways, these things kind of go into modules, and then those go into like a unit that sits either like on top of the car or just kind of behind the windshield. So these are components that our company is also making. All right, changing courses a little bit. So we can also use photonics to not just like visually see the world, but we can use it to infer about other, particles, let's say within the universe. This is an image of the Large Hadron Collider. I'm sure you've all heard of it by now. So how does photonics really sort of play into this? Well, the way that these systems work is that they speed up protons to very, really high energies. They smash them together, and they have cameras basically that look and see where do these particles go. All right. When you speed these particles up, you know what energy they're at, but you don't know necessarily the mass. In order to know the mass that will tell you the particle, you need to know what trajectory did it take. It's like smashing two billiard balls. All right. If you maybe you don't know how heavy they are, but you know how much force that you gave them, and you can measure what angle they come off of each other. That tells you something about their mass. Well, you need really, really, really large cameras that can track all these particles that go in different directions. And so if you know the energy of the two incoming particles and you can measure their trajectory, you can infer what their mass is. That is how they find new particles. In order to find lighter and lighter particles, they need higher and higher energy, and they need to smash lots and lots of particles together, because it's really hard just to see one instantaneous event. You need millions, billions of events that you can say with high statistical confidence that you found something new. So this is a lot to say that in order to track that information, you need to be able to get information, i.e. like where are these particles going? You need to get that information away from these large detectors and process that information somewhere else. So this is delving a little bit into what my PhD research was, which is you can actually do this, or at least the hope is that you can do it. It's not being done today quite yet. You can actually use optical interconnects and place these sensors really close. So this is like, this is the Atlas sensor. This is a CMS detector. These are both an LHC today. They do use actually fiber optic interconnects, but they're actually kind of slow. And so what I was proposing was how can you kind of speed this up? And there are different ways that one can do it, but I thought it'd be kind of interesting. Actually, I went to Fermilab. This is actually in 2019. So to give you a sense of scale, this is actually like a life-size sort of cross-section of the CMS detector. So you can see me there, and where these detectors really are right here, like in the center. So a lot of radiation. You would never survive a second if you were that close. You know, there's just way too much radiation. So the challenge becomes, how do you make components that can survive those kinds of environments? So one application for where photonics is actually helping the high energy physics community to find and discover new particles. All right, we're gonna go away from the Earth a little bit here. So we're also utilizing photonics in space, and this is really to well, that one didn't come through. It's really to investigate what's going on in the atmosphere, right? We know there's obviously oxygen, there's nitrogen, but there's other, you know, elements up there that are, you know, of interest for global monitoring, right? So methane, CO2, and it turns out that these molecules, they resonate at particular wavelengths, and we can use infrared light actually to perturb them and look at the return signal. And based on, basically it's LiDAR again, but in space, we're looking at the return signal, and how much of that comes back can tell us about the concentration of those compounds. So we're looking sort of around this 1.6 micron band, and it turns out that when you zoom in, you're looking at, you can see all these molecular vibrations that correspond to absorption. And so we can look at carbon dioxide, we can look at methane. That's all great. And the intent, this is work that we're actually doing with NASA today, is to put these types of lasers in space so that you can orbit around the Earth and you can make lots of measurements. And so where Freedom comes in is that we make tunable lasers. These lasers actually allow us to look at multiple resonances or multiple elements and kind of collect all that information simultaneously. I don't know if this video is going to play, but we'll give it a shot here. Probably not. But anyways, what this video is actually going to show you is that it's already been done, that NASA has launched some satellites basically to go up in orbit and monitor, actually, in this case it was going to be carbon dioxide concentration, not only as a function of like geography, like across the Earth, but also as a function of time. And the intent is that we can actually use the lasers that we make, and we can collect sort of all that information simultaneously. So unfortunately, that video isn't going to work. But yeah, like I said, we're kind of doing this today. We just got a very large program from NASA this past year to continue sort of this work. So it's very exciting, and I think Jürgen will be working on that at some point. All right, so some other uses for photonics, again, sort of a sensing application. So this is delving into gravitational wave detection. So there are multiple observatories, right, that are kind of spaced across the US in this case, and they are looking at perturbations sort of in very, very long cavities. These are like, I forget exactly how long they are, but a few kilometers, I think, these arms. And so they're measuring sort of differences in path length as a gravitational wave basically kind of perturbs that. Again, well, this will be a video that probably won't play, but it doesn't matter. Basically, you know, these detections have been made. Gravitational waves sort of are real. Will this work? Yeah, as I just described, you're looking at sort of an interferometer, right? This is a really large version. We actually also make these at the microscopic scale. So the chips that I was kind of showing earlier operate sort of on a very similar principle. You can manipulate light on those scales, and you can use that either to do sensing, or you can also use it to do modulation. So where do we come into this? Well, we're actually part of a program that's called LISA. So this is a laser interferometer space antenna, and we are developing the lasers that will go into, well, a laser, there's multiple lasers that will go into this type of system. So this is a very, very, very large interferometer, much larger than LIGO, because the longer sort of you have these arms, the smaller wavelengths that you can detect, and therefore you can detect very faint, you know, gravitational wave signals. So pretty exciting. I think this mission is, you know, very likely to happen, but you never know what's going to happen with NASA's funding. But Actually, it's an ESA mission, but NASA is contributing as well. But we're very excited to participate in that. Okay, continuing on the space theme here, this is actually being done today. I don't know how many of you have heard of SpaceX and Starlink, but there are, I think they're up to about 3,000 or so satellites in low Earth orbit, and they are all connecting to each other and talking using light, using lasers, basically. So why is that? It's because you have a huge amount of data that needs to be pushed around the Earth, and typical RF and microwave links just aren't fast enough, basically, to do that. And they're also leveraging a lot of the technology that's being used today, like in the data center, because it has very low cost. There are these millions of these components that are being made today, and they're able to actually put these on satellites and launch them up. What's actually interesting is this idea, this concept is not novel. This has been going on for many, many decades. And we've also kind of dabbled in this space for some time as well. This is some of my also early work that I'd done a few years back. But the idea being that you can make the transmitter and the receiver all as those little chips I was kind of showing earlier. And you can put them into pretty small packages, on the order of about 30 millimeters or so, and you can get very, very, very high information capacity with them. These are just kind of more examples of things. It's the actual devices themselves, but what you are doing is actually transmitting information not only by turning light on and off. Okay, I think we're all familiar with that, but you can also change the phase of light as well. So just like an ocean wave, are you in a peak or are you in a trough? There is a phase basically associated with that. And so what we're looking at is information that's being transmitted here in both of those dimensions. So there's a transmitter, there's a receiver. I don't know, I find that pretty exciting. Okay, the final part of the talk, reducing energy. So we were kind of talking about this in the beginning, that these transceivers, fiber optic networks, it's all being really driven by massive data consumption, right? A lot of YouTube videos were being streamed live. This talk is going through one of these data centers somewhere. The problem becomes, as this data increases the capacity, like imagine you need a nuclear reactor next door to your data center to run it. That's just not really feasible, maybe, I don't know. But it's a huge amount of energy. We're talking many tens of megawatts to be able to, what you would normally run a small city with. That is what these data centers are kind of consuming in terms of energy. And most of that power is actually being attributed to the photonic interconnects that are running. Obviously, there's huge cooling challenges as well. But if you can make more efficient optical components, you can drastically reduce the amount of energy consumption. So the problem is that as we're fighting two kind of competing factors. One is that we want to increase the amount of information that we can transmit, but we also want to spend less energy doing it. So this is a very challenging problem, and there are a lot of companies out there who are trying to actively solve this problem, us included. And Jürgen will recognize this, but we're actually making laser sources that can be multiplexed together and have multiple colors of light in a single sort of device. Why is this interesting? Because you can actually reduce the amount of energy that's consumed. In this case, that's primarily attributed to cooling it. If you had a bunch of these little lasers, they're not 100% efficient. If you put a bunch of current into this device, maybe 50% of that in the best case, more like 25% of it, will actually be converted into light. The rest of it just goes to heat. So this is a big problem. So when you have a bunch of these, if you remember, I was calling them these butterfly packages. I mean, those are what are actually kind of used today. And if you have one laser per package, that doesn't scale very well because you're consuming a lot of power. So electrical power. So if you can put this all into basically one module, there's a pretty good amount of energy savings that you can create there. The analogy that's kind of being made is it's almost like an optical battery source, right? You have a bunch of these optical interconnects. They all could have their own dedicated laser, each one of them. Or you could have one laser and it basically supplies many of these interconnects. So there are savings by basically consolidating your resources, essentially. So this is one thing I guess I wanted to point out. It's kind of fun. The way that we're doing this is we have an array of lasers. Again, these are, millimeter scale type devices. It's not kind of coming out here quite well, but there is like a glass type circuit that is able to multiplex all of these colors together, have them mix and be replicated at each output. So if I have 16 different colors, there's 16 outputs. Each output has all 16 of these colors. And all of that goes into an optical fiber array, and out it goes into the world. And the way that these components are actually connected together are these things called photonic wire bonds. Now, maybe some of you are familiar with electrical ICs, and they use gold wire to connect an IC, to some printed circuit board or something, right? So that gold wire is about 25 microns in diameter. These are optical waveguides, so they behave similarly. They transmit light, but these are on the order of about 2 microns wide, order of magnitude smaller, right? And it's pretty fun. It's actually, this is a tool that we have at our facility. It's a 3D printer. You put down sort of a polymer. There is a laser that's used to cure the material in a 3-dimensional volume, and you're able to 3D print optical structures. So these can be used to connect. Think of it like Legos. You want to connect a laser to some other chip? Great. You can actually do that by 3D printing a structure that optically kind of connects them. This is kind of a unique capability. We're one of the few companies in the world that has this, but it's also, I think, pretty exciting, and I think it shows great promise for being able to do many different things in a single type of package, rather than trying to force all of these different functions to be done in kind of one simple device. Maybe you take a divide and conquer type approach. If I have a really good laser, maybe I don't want to put a modulator on there or a detector. I can keep those chips separate, and now I can connect them using something sort of like this. Anyways, I went through that pretty quickly, but thank you all for your attention, and if there's any questions, I'd be happy to take them. Yeah.
Thank you.
So now you're all experts in photonics, right? Now you can give this exact same talk.
I had a question.
Yeah.
About the tunable nature, you're designed to sweep, I think I saw about 50 or 60 nanometer.
Yes.
And is that how you're getting your QPSK modulation? By tuning the phase, one high, one low, and you achieve that QPSK chart I saw?
That's not how. Go ahead.
We don't have a room mic, so if you could repeat the question.
Oh, right. So the question was kind of looking back to some of the. Yep, here we go. Like here. How is the quadrature phase shift key modulation being done? So actually, there is a tunable laser here, but the idea is you're actually using a grid, and there are specific channels. Okay, let's make an analogy to a radio. There are different stations, right, that are each separated by a particular frequency, right? So when you're tuning the dial, I don't know, I still have a radio in my car, so I still listen to the radio, but right, some of us remember. When you're tuning that radio, right, you're actually scanning through particular channels that are separated by a specific frequency, right? That same type of plan or approach exists in the optical domain. So red corresponds to a particular channel, green, blue, whatever. These are all different channels that one could communicate on, okay? So that's not how the modulation is being done, but that is, the tunable laser is there to be able to transmit and talk on different channels. The way that the modulation is actually being done is in this device up here. Okay, so you remember I was talking about how you can make this large interferometer and make it on, the micron scale. That's what this is. Okay, we have light that's actually going, if you just focus on maybe the top half here, you see there's two arms that are kind of running in parallel. What I'm actually doing is splitting light into two paths. Well, it's really four here, but let's just simplify it and talk about one half of it. I'm splitting light into two paths, and by injecting current, actually, into one arm, or voltage, what I'm actually doing is changing the refractive index of the material. And by changing the refractive index of the material, I'm changing the velocity of that wave that's traveling through. So I can either make it go the same speed, or I can slow it down. And by making it go faster or slower, I'm actually changing the phase. Okay, the light in these two arms propagates down, and then they recombine. If they are in phase, they add up. If they are out of phase, they cancel each other out.
So the information is applied to the current on those pathways.
Correct. Yeah, so you can imagine there would be electrical signals that kind of come, well, these are transmission lines, but this would connect to something like an FPGA or something like that. It's sending these high-speed electrical signals in, and those then are applied to a device that then modulates light. But it's really because of changing the material properties, and the light that's passing through it sees a different material depending on whether you're applying a current or a voltage, and by how much. You know, I could slow down light maybe by a lot, but if I have a large current that goes in, or I can only change it by a little bit if I just put a small current. So that's the simple answer.
Then you have the usual communication kind of issues with synchronizing
Sure.
that to the data flow and then on the receive side.
Absolutely. Yeah.
I
could talk all day about how this experiment was actually done and the problems of synchronizing all the data. Yeah, for sure.
Next meeting's in your lab.
Yeah. Yeah. Actually, so the way that these images are even actually generated, this is all information that was captured like on an oscilloscope. And then I had to write a program basically to like deconvolve all the problems that were associated with it. So it's post-processing basically. And so timing and alignment, all those things are critical. Yeah, absolutely.
Now that current control of delay, that's not how you get the different colors. You mentioned later on that you get more of a spectrum out of a single laser.
Yes.
How is that done? Is it the same technique or you have same delay?
Yeah, so it's a similar, the physics is similar. So any laser has basically three elements to it. Well, I guess technically maybe two, but we'll say three. It has a gain medium. So you need something that can, you know, you could either put in more light or you can put in more current and you should get out more light because of that. Okay, so there's a gain medium that's involved. You need to put this also inside an optical cavity. So then you need two mirrors. You need light that can basically bounce back and forth. And it builds up in intensity because you get, you know, again, in phase round trip delays and you get a buildup. Okay. Depending on how big that cavity is, that could determine what color of light I get out. Yes. Well, there's more to it than that. In this case, what I'm describing right now, I might get a lot of different colors out at the same time. And it also depends on like how broad of a spectrum that this gain material can produce. Okay, I'll give you an example. An LED. Actually, the gain materials that we make, if they fail as lasers, they're really great LEDs, right? So when we look at an LED, we think, wow, that looks like it's really pure light. It's actually not. It's actually a very broad spectrum. It could be on the order of about 100 nanometers wide, okay? And so what you actually need inside of that is mirrors or filtering elements that'll only force it to laze at one particular wavelength, very pure wavelength. So we say that LEDs are kind of incoherent light, whereas lasers are very coherent. You're only producing one very pure spectrum of light, okay? Now, the way that the laser is tunable is that these mirrors are actually done by etching gratings. I don't know if you've ever seen like a diffraction grating. So actually we all have probably, some of us might remember, compact discs. Compact discs have, if you look at them and you know, you get like a rainbow effect. Why is that? It's because you're taking in white light, you're getting a diffraction off of it, and so depending on what angle you're looking at, you're getting different colors, right? Some of the early lasers actually were based on that very same principle. You use a diffraction grating, which also works as like a mirror, and depending on the alignment of these mirrors, you can select a particular wavelength that you want it to laze at. But again, we're talking, you know, tabletop size devices. So how do we translate that into a device that looks, you know, like this? Well, what we do is we etch similar grooves into a waveguide, and a waveguide is well, okay. A waveguide is basically comprised of three elements, I guess. You need sort of like a core material that has like a very high index of refraction, surrounded by a material that has really low index of refraction. So like an optical fiber, if you were to look at an optical fiber, there's like a little dot in the center, and there's a mode that kind of propagates through. If I etch that material sort of around it, if I perturb it, it actually acts like a mirror. I get reflections that actually, light goes down and some of it will actually bounce back. Okay, so if I now have these etched gratings into a waveguide, I can now create really, really small laser cavities. And because it's made of the same material, by injecting a current or voltage into this material, I change the refractive index of that grating, and therefore I change what color is actually reflected back. Okay, but I'm doing that to both mirrors actually now.
And you can control that diffraction with like a voltage applied to channels, something.
Yeah.
I've seen something similar.
Yeah.
Okay.
You could apply a voltage. Well, we generally use a current, but yes, you could.
It's like almost like, I remember speed being an issue on that, not changing that fast.
Mm-hmm. So actually, that's a good question, because these devices these devices also, you can think of them as being diodes. These diodes have very small resistance and also very small capacitance. So if you look at it from an electrical perspective, for those of you who are familiar with like RC time constants, these are really, really fast. These are nanosecond type time constants. So
It's larger, it starts to build up.
yes,
Surface area.
the surface area, which will contribute to the capacitance. So yes, there will be limits as to how big can you make this thing, and so there's a trade-off, right? Because if I make it really long, turns out actually I can get away with putting really small voltage or currents to make a large change. It comes at a cost. I've now made a really large capacitor, so it's going to be slower. So, you know, depending on the application, what do you care about? Do you care about the efficiency of that device, or do you care about speed? It depends, right?
Okay, thank you.
Yeah.
I'll let someone else. If not, I got another question.
Keep them coming.
There was a moon project.
Yeah.
That's pretty wild.
Or-
I know moon dust is the issue, and we got, you know, if you talk about optical paths and this terrible fine soot-like dust. Is anyone talking about that?
I'm sure there are. I'm not as, you know, well versed sort of in moon dust, but like for instance, but like if we bring it back basically to like Earth, right? So one of the big problems for doing satellite communication, the biggest problem is actually not satellite to satellite. It's actually satellite to ground. Can you imagine why?
Besides that.
The atmosphere.
Fog and atmosphere and
Yeah,
Cloud cover.
cloud cover.
putting on the angle of the atmosphere.
Yeah.
Cloud
The-
cover
the-
probably
the-
refracts
the-
the crap out of it.
The problem, exactly. The problem is that clouds are actually, the infrared light is well, clouds are opaque at infrared light. So when you have a satellite that's orbiting and you're trying to establish a downlink and send information down, it turns out that it's very, really challenging, because how many places on Earth are there where there is minimal cloud coverage? There's only a few, and that's where those ground stations are located, high in the desert, really low moisture areas. And so it's not just dust, which are actually particulates, but even water vapor is actually a problem. So you can think of it as either being it could be a feature because you could measure cloud coverage and you can see how much water vapor is there. But if you're trying to establish an optical communication link, that's a problem. You have loss in that channel, and now you can't talk.
But for the moon, no, that wouldn't be the issue.
No water vapor up there.
No water vapor, but if there are reflective particulates, you'd still have to account for that some light is going to not make it to the detector. Basically, it's going to get scattered somewhere. So that has to be considered when you're designing your link, that you have enough margin, assuming that you're losing photons because of particulates.
From the moon.
Well, on the moon, you should only have that to actually have the thing move, because normally there's nothing blowing, there's no atmosphere, there's nothing going to be moving anything unless something is out there moving around. Yeah, it's not. There should be zero dust
Perturbance.
moving,
No perturbance.
except anything that may be coming in new or whatever.
But then there's a lot of issues around that dust. Somehow it gets around and
It gets stuck in stuff, it's so small, and it sticks in things, and the gravity isn't high enough to like pull a lot of that stuff off, so it stays wherever it sits.
So you said you do like the satellite to satellite communication is the same communication that you're using for connectors and switches and stuff and network stuff now, or like how do they? Is it just like how do you align between satellites with tiny little lasers?
It's very challenging. So they're actually telescopes. They are telescopes. There's these optical terminals. Have these really large lenses. They're apertures. I mean, they're probably about this big, and it's really difficult when these are many thousands of kilometers away. So they go through different phases. So there's like a phase where it's just like a beacon phase. It's just like a lighthouse. Like, here I am, and the satellite is kind of looking around. Oh, okay, I see you. And then it sends another laser to start establishing like tracking. So, all right, I know generally where you are, but now if I'm going to send information, we need to actually lock into each other. So there's like an acquisition sort of phase. And then once they are well aligned, and it's a really hard problem, then they can establish a communication link, and then you can have bidirectional traffic. But the components that are being used that like feed into that system, they're using optical transceiver components that are about the size of a stick of gum, and those are like I don't know, $10 a pop or something, and they're like putting out 100 gigabit per second to data rates, but it's a problem in that you can't just take any old component because there's also radiation to contend with still in low Earth orbit, and so they go through great lengths, is what I'm told, to find suitable off-the-shelf components that they have to do a very minimal modification to survive in that environment.
So are they using a telescope on both ends? For
Yes.
the sending and the receiving?
Yes, absolutely. Yep. Mm-hmm. Yeah. So basically, whatever it is, every week or something, when a rocket goes off at Vandenberg, there's like 100 of these Starlink satellites usually on one of those. So
There's a fair amount of things that are space qualified tend to take a long time to get that way, and has to be some impetus to do that, and it takes a lot of time to go through all the testing. So there's a stuff which is established, which is space qualified. If you want to do this other thing, then you have to go through 10,000 cycles. I work at a company where you use solar panels for
Oh, yeah.
spacecraft, and the company we built this thing for wanted to do 80,000 thermal cycles on solar cells. And so it can be done, but you have to qualify it and do then we didn't need that any address radiation, it just addressed thermal cycles.
yeah,
So
thermal is huge. Yeah.
eventually a lot more stuff will be space qualified for that.
Yeah, it takes a lot of time and a lot of money to be able to do it. So someone like SpaceX, they can front the bill to kind of do that
Or
stuff.
just put up, in SpaceX, you might just put stuff up there and see if it lasts up in space.
Well, so that's an interesting comment because what are the lifetimes of those satellites? They're only like what 5 or 7 years, something like that. They're less than 10 years. And then there are other constellations that are only designed to be up there for like 2 years. So even if they will degrade, they're not meant to be in that environment. That's okay because they're gonna essentially burn them up and launch new ones that kind of put up there. The world that we kind of live in, more like what's used in telecommunication equipment, those have to be qualified to survive for something like 20 years. So it's a very different problem and really unique one because you can do things that you normally maybe wouldn't be able to do because the lifetime is actually going to be pretty short. So.
Two questions. One, why is it called Freedom Photonics?
Because it's free. No.
Is it like an open source or is it like I don't know what's the?
No, I think so. When the story that I'm told from the founders is, we do a lot of work with the U.S. government, and this is sort of around 2005, sort of the Iraq War and everything, and so they're like, wow, we stand for freedom. And so, but at the same time, the idea was that we could implement a lot of different functions basically within the optical domain. So you kind of had the freedom to kind of choose what is it that you kind of want to do, right?
The other one I recently read, it's not that recent, maybe 6 months or a year ago, this result in like photonic communication. It's about like having a noisy channel or a channel that like perturbs your wavefront because what they're trying to do is communicate. It's like where they basically like shape the spatial modes of the light
Mm-hmm.
so that they can send like 1 of 16 symbols at every pulse, right? But it's very difficult because they have to go across such a noisy channel that has maybe variations in index of refraction and stuff, and so it'll be like going through privacy glass, in the atmosphere or anything. So it's
Mm-hmm.
basically restricted only to the right types of fibers. Except they found that instead of doing like the symbol approach, there's some other property of light, like its vectorness, that remains the same and can take on as many values, but is not perturbed by the medium it travels through. So they can even shine it through through flesh without, when still being able to recover what was the original symbol, on every pulse or something. I'm wondering if maybe that's something that you guys are aware. It was some breakthrough result, a little while ago.
Yeah, I'm not an expert sort of in that particular domain of things. I think if I were to take a wild guess, it's probably like the orbital angular momentum that they're kind of talking about, and they kind of look like vortices that kind of travel together.
Right,
Yeah. That's about my limit of knowledge of that. That's about it. But yeah, it's a problem that whether you're going through the atmosphere, whether you're going through dust, whether you're going through the water, there's actually undersea communication channels. All of this equates to loss. It could be noise, but at the end of the day, you're just not being able to detect sort of the photons. So there is a lot of work, and there are a lot of new approaches basically on how do you overcome some of these physical impediments. And so whether you change the color of light, whether you change the polarization of the light, whether you change the phase of a light, and now I guess they're changing the orbital angular momentum, whatever that means, of the light. These are all like, they're called degrees of freedom that can be used to encode information and decode information, right? So.
Would that be a processing step that happens at the transmit and the receive side, or is that just a receive processing of the signal?
I believe so. They're not using a physical degree of freedom. They're using some other property that's computed using some real degrees of freedom, and they call it vectorness or something. But yeah, so it's basically like the way that they emit the light, and the way that they decode, the way they reconstruct and categorize the symbol was intended, is when it's more robust than encoding it in polarization or in like the twist of the light or in its amplitude.
We have a question from the internet.
From the interwebs.
Yeah. What do they use to steer the optical beams for the inter-satellite links?
Yeah, so today they're using like gimbals to be able to, these are very much mechanical systems to be able to point that beam. So you can think of it as almost being like on a tripod, so to speak. There are challenges associated with that because you need basically a motor to be able to move it, but these motors don't have the most smooth movement. So they have some jitter associated with it. So this is like a big problem, right? So even there's been, I'm not an expert in motors, so don't ask me more questions on this, but there's been a lot of work basically into make like really low noise, low vibration type motors to drive these gimbaled systems to be able to move a telescope. Like looking ahead, what people want to do is to not have any non-mechanical movement, non-mechanical beam steering. So this is actually done today in the RF world, where they used a phased array antenna. And so you have multiple antennas, and it can be a 1D array or it can be a 2D array. And you can basically, again, by using how in phase or out of phase are these beams, you can steer sort of the RF beam, and you're not actually moving anything at all. You're actually just changing the phase of that wave, and that'll determine sort of in what direction do you get constructive interference. The same type of technique is actually being applied to light. And so we're using a diffraction grating again, I mean really. And so they're shining light out of a chip, and it comes out of the surface. And then by changing the refractive index of this grating, they can move where that light goes. And so they need to be able to change the direction of light in both dimensions. And they can actually do optical beam steering and point it in the right direction. It's very, very, very challenging.
Lossy. It's a very lossy technique.
And it's very lossy. Yes, absolutely. So today it's being done mechanically to like move, these telescopes, but there's a lot of intense research basically and to eliminate those mechanical systems and just do it purely optically. Yeah, good question. All right. Well, thank you. Appreciate it. Yeah. No tomatoes or lettuce were thrown this time, so that's really good.
I never thought that like you could test electricity through something, through some sort of optics, and it would change everything. It would actually like affect diffraction and different things like that. That's interesting.
Yeah. So there's
changing an angle on like the physical idea would be like changing the angle of a prism to some extent.
Well,
But in a totally different way.
you're
I can't remote control it. So it's like
Lines of crystal material, and then you have a gel material, so it's a fluid
Okay. Yeah.
That's what it's enough.
Gotcha.
yeah. There's different physical phenomena that will result in